Let me first start by thanking you all for choosing to be here and to hear us talk about how to secure how to secure code and data in use with AWS confidential computing capabilities. My name is Arvind, and I will be jointly presenting this session with JD Bean, Principal Security Architect, and Sudhir Reddy Madhulapalli, our Specialist SA responsible for confidential computing at AWS. Here's the agenda for today. We'll start by first sharing our perspective on confidential computing, and then we'll introduce some of the core capabilities that enable confidential computing along with EC2, starting with our AWS Nitro System. Then we'll introduce AWS Nitro Enclaves and NitroTPM. We'll then switch gears and deep dive into AWS Nitro Enclaves and talk to you about the key benefits and features. Then we'll piece it all together with a sample data flow to show you how data flows from a data lake into an enclave and gets processed securely inside the enclave. We'll then touch on some of the use cases that we are seeing in the market today and where we expect the market to gain traction in the next year or so. We'll close the session out with an introduction to NitroTPM and UEFI Secure Boot. So what is confidential computing? Before I get into confidential computing, can I see a show of hands? How many of you are familiar with the concept of confidential computing? It's getting bigger and bigger. You know, the crowd is growing. I'm glad to see this community grow, right? So let me share AWS's perspective on confidential computing with you. At AWS, we define confidential computing as the use of specialized hardware and associated firmware to protect your code and data from any unauthorized access while your data is in use. That's the key to remember. It's while the data is being processed. The methods to protect data at rest and data in transit have been out there for a while and pretty mature. This is about protecting the data while it's being processed in the CPU. Why does this matter? It matters because if you're running highly sensitive data processing in a standard EC2 instance, there is a possibility that somebody who has access to the instance also has access to the data once the data is decrypted and revealed as plain text to the instance itself, even though it's only done during compute operations. So that's where we draw the distinction for confidential compute, where we emphasize more on protecting data while it's in use. In talking to customers, we have identified two different, distinct security and privacy dimensions from which code and data needs to be protected. Dimension one is about protecting the code and data from operators on the cloud provider side. That will be AWS in this case. And dimension two would be to protect sensitive code and data from customers' own admin level users or from malicious actors who could pose as admin level users and gain access to data. So those are the two different dimensions that we are most concerned about when we talk about confidential computing. And the different capabilities we bring to bear with it can be segregated into two different types of environments. One is a rich compute environment, which is fully accessible to you as the customer and not accessible to any of the operators on the AWS side. So that addresses dimension one that I talked about. And the second type of environment we provide is a highly restricted environment, which actually shuts out access for everybody, including yourself, including admins on your side, who don't get to access the data once it's dropped inside that environment. And that addresses dimension two. But why are we talking about all this today? Why does confidential computing even matter? Right? It matters today because the amount of highly sensitive data that is being processed and managed in the cloud has gone up significantly. And as that has gone up, so has the stringent requirements from customers who are processing this data, who are subject to other regulatory requirements themselves and have higher privacy and security requirements than they've had in the past. So what matters more when you think about confidential computing is what is it that you're protecting and who are you protecting from? So what you're trying to protect when you adopt something like this is highly sensitive data, and who you're trying to protect it from is addressed in those two dimensions I talked to you about. So some of the sample set of data that you could think about that you don't want to reveal to anybody would include personally identifiable information, healthcare information, digital assets, cryptocurrencies, encryption keys, and so on. Those are just a smattering of some of the data sets that you could be dealing with. There's a lot more, of course, right? So now you know what we're protecting. You also know who we are protecting it from. But how do we do it? We do it with the capabilities that you're seeing here. Number one, the AWS Nitro System. AWS Nitro System is the foundation of all virtualization for all of our Nitro-based instances. That is pretty much majority of all the instances that we have released in the last 4 to 5 years. That addresses dimension one. By adopting Nitro-based instances based off of the Nitro system, you're already getting an assurance where none of the operators from the AWS side can access your code and data that's running inside an EC2 instance. That's an assurance you're getting by default. That's a protection you're getting by default when you adopt a Nitro-based instance for your computing capabilities. The second big one here is AWS Nitro Enclaves. AWS Nitro Enclaves provides a hardened and highly constrained virtual machine which addresses dimension two, whereby it shuts off any access even for admin level users on the customer side. And lastly, NitroTPM, which allows for cryptographic attestation that helps you establish trust between your instance and any other compute entity or otherwise that you're trying to interact with. And that again addresses portions of dimension two. So we're going to deep dive into all of this today and discuss a little bit more about how they're implemented and what it means to you in terms of use cases and workloads and how the data flow looks like. I'm now going to turn it over to JD to talk to you about the Nitro system.
Hi, all. So, as a reminder, right, the Nitro system, the AWS Nitro system, is the underlying technical virtualization system that powers all of our modern instance families for Amazon EC2. The Nitro system is, I use the term very specifically, is a series of components that work together to provide this service. And it's the result of a sustained multi-year long journey and investment to reimagine and reinvent virtualization for the cloud, right? And the guiding light in that process is very much security and confidentiality. So to understand a bit about what the Nitro system is, I think it's useful to take a brief moment to discuss what classical virtualization looks like in order to compare the two. So in this diagram here, you'll see on the left-hand side a representation that I think is probably a fair high-level drawing that many folks might draw if asked to sort of represent what virtualization looks like. You have a host, a server, right? A main board running something like an Intel or an AMD server class processor. And running on that processor, you've got some software. Probably the number one most important software to call out here is the hypervisor, the virtual machine manager that is responsible for the core of virtualization functions, right? That's translating between and managing resources directly on the system, such as access to the CPU and system memory. You've also got a few other pieces of software, right? The hypervisor virtual machine monitor are relatively small, straightforward pieces of software, but you need a lot of other things to provide a modern virtualization stack that customers will be delighted by. Right, you need things like networking I/O. You need storage, right? In the case of EC2, that's something like both instance storage and network-provided EBS storage. Right, you also need management, security, monitoring, and orchestration. Right, the things that make cloud cloud. all of these things in classical virtualization run on the same system, right? The networking, the storage, management, security, monitoring, all of these functions typically have been implemented in a privileged copy of a general purpose operating system. In the Zen world, we might call this DOM0. For other virtualization technologies, it may very well have a different name. This DOM0 is a much heavier weight, much richer piece of software, right? Not only are we dealing with device drivers and device models to emulate input-output calls, but we also have that full software stack on top of it. When you take a look over on the right-hand side, you see what the Nitro system looks like today. And it's dramatically different in a very clear way. What was once a single physical host, a physical system, has been broken up into two separate logical domains that have a physical separation between the two of them. So in this case, what we've done is removed the networking, the storage, the management, security, and monitoring, all of those features and functions that traditionally would have run on the system mainboard, and we've moved them off onto dedicated pieces of hardware and associated firmware to provide each of those services directly to virtual machines. Left on the EC2 host is a slimmed down hypervisor. It's KVM based, known as the Nitro Hypervisor. And the rest of the main system board is devoted to running customer virtual machines or EC2 instances. So how did we do this? What are the key components of the Nitro system? There are three key components. First are the Nitro cards. The Nitro cards, first off, there's a Nitro controller, and then a series of dedicated cards, independent computers and systems on a chip that are custom built and designed by Annapurna Labs, our in-house chip design capacity, for each of our dedicated functions here. We have local NVMe storage for instant store. We have an elastic block storage device. And we have networking, monitoring, and security functions as well, doing things like validating our boot system of our Nitro control cards, interacting together and orchestrating over secure and dedicated channels between each other. The Nitro cards extend their control and their involvement in the main system board through a special piece of hardware called the Nitro security chip. This is a device that is actually installed on the system mainboards of our hosts. It allows the Nitro controller to extend its boot checking and validation onto the system mainboard, right? So when hardware resources are started up, right, we are able to ensure that no processes that run on the system mainboard are able to write to non-volatile hardware resources and storage. And we're able to validate on boot time that our system is in a trusted, a known good state. The last component is the Nitro Hypervisor that I mentioned earlier. And this is a very special piece of software. It is extremely lightweight, it's slim, and it is extremely high performance. It provides nearly indistinguishable performance from a bare metal system. It is not a rich and multi-purpose operating system environment. We've removed all unnecessary components, kernels, file systems, network services. None of these are included in the Nitro Hypervisor system. And also of interest and particular note is that the Nitro Hypervisor is an optional component. In our bare metal systems, the Nitro Hypervisor isn't even involved at all. We're able to use our Nitro cards and our Nitro security chip to provide an experience that is almost identical to launching a virtualized EC2 instance directly on raw bare metal hardware. So here's another kind of abstract view in a sense of really what EC2 really looks like. We have these two separate domains, right? These logical, physical domains. On the left is that server, right? This is where customer workloads and VMs are running. And this server, as we mentioned, has no local file system. It has no network connectivity at all. It is entirely isolated and communicates only with the second domain, the Nitro cards and controller represented on the right-hand side. there's no interactive access of any kind on an EC2 host server mainboard. There is no mechanism for it. It does not exist. On our Nitro controllers and control cards, which do have a network connection into our EC2 service, there is also no interactive access mechanism of any kind. The only access that is able to be provided to the Nitro system is through the Nitro control cards via authenticated, authorized, logged, and audited APIs. And there is no API or mechanism in this system for an operator to access customer data on encrypted EBS volumes, encrypted instance store, or on EC2 system memory. All of this is the default confidential computing that comes with using a Nitro-based EC2 instance. So what then is Nitro Enclaves? How is it different? How does it relate? So Nitro Enclaves addresses, I think, right, that second dimension of confidential computing that Arvind mentioned earlier. It takes a scenario where customers within their own EC2 instance have their users, third-party libraries, applications, and rich operating system stacks running all together alongside their most sensitive data. Users here I'll mention could be an external user, maybe accessing a web application, but it could also be your most trusted administrators, like a root user. What Nitro Enclaves exists to do is to bring the power of developing architectures similar to what we've done with the Nitro system in your own EC2 instance. You're able to develop that isolated compute environment where you're handling your most sensitive data and separate it from any capability of interactive access. You can now build applications that have this same breakdown between trusted and more trusted security domains connected via a local communication channel. So before I hand it back to Arvind and Sudhir to talk a bit more, I want to cover just a few quick technical points about what an enclave is and what it isn't.
There you go.
Enclaves are isolated, hardened, highly constrained virtual machines. Although an EC2 instance creates an enclave, and we often call it a parent instance, the two are also peers. An enclave does not run within a parent instance, it runs beside it on the same system. An enclave is independent from the parent, running its own lightweight Linux OS, independent kernel, own encryption keys, own memory, and own CPU cores. It's not a container. It has no persistent storage. By default, it has no administrator, root, user, or operator access from the parent instance of any kind. And it has no external networking. Its only connection to the outside world is over a local communication channel back to the parent instance that created it. That local communication channel is called a VSOC, and you can think of it as a virtual serial cable that connects the enclave back to the parent.
Thank you. So you just heard JD introduce Nitro Enclaves to you, and it sounded a lot like when he concluded that, he told you so many things the enclave is not. It doesn't have storage, it's not a container, it doesn't have network access, no interactive access. So why would you use an enclave? Right? We just told you so many things it's not and what it doesn't have. Here's why you would use it. Here are the key features and benefits of using Nitro Enclaves. Number one is additional isolation and security. So we talked to you about the Nitro system, which provides a certain degree of isolation between your code and data and us, preventing us from accessing any of that. What Nitro Enclaves gives you is additional isolation beyond that, not just restricting us, but even yourself from your code and data, thereby making sure that whatever you're processing inside an enclave is securely processed from anybody ever being able to look at it. It communicates through to the parent instance through that secure vSOC channel that JD talked to you about. So there's just no other communication channel, no way to interact with the enclave, no way for you to go SSH into it and snoop around to see what's going on. Second big benefit is flexibility. It is processor agnostic. It's based on our Nitro system, but it's not based on any specific CPU. So you could have a fleet with different CPUs in it, and you could still bolt on your Nitro Enclave solution without having to worry about what CPU is running in the background. Today we have Intel x86, AMD, and Graviton CPUs, and technically we're capable of hosting the Nitro Enclave solution on any of that. So it's processor agnostic, thereby making it very, very flexible for you and not tying your solution to any one type of microarchitecture that dictates CPU-based applications. It is also flexible in terms of how you allocate resources, the memory and CPU resources for your enclave from your existing EC2 instance. So as was explained above, you could spin off an enclave from your existing instance by dedicating certain resources to it. How much of that resources you want to dedicate really comes down to the workload in question. What is your use case? How much CPU resource do you really need? How much data payload are you dropping into that enclave? Those are all going to determine how much CPU and memory you need. And based on that, you could simply dial up and down how much memory, how much CPU are you dedicating from your existing instance to spin up an enclave. And lastly, cryptographic attestation. The enclave has the ability to prove its identity and prove that only authorized code is running inside the enclave. So if you have an application that's processing sensitive data inside the enclave and you want to be really sure that is the application that's going to see the data once it's dropped inside the enclave, you could start by using the enclave's cryptographic attestation capability to prove, number one, that is the specific enclave that should be receiving your data. And that is a specific application in the enclave that you are expecting to see to receive, decrypt, and process the data inside the enclave. Enclaves also come with first-class integration with AWS KMS and AWS Certificate Manager. We'll touch a little bit on both of that as we go through the rest of the session today. So the enclave's ability to prove its identity, what does that really give you, right? It's the ability for this enclave to come out and say, look, I am enclave A, and here's the proof that I am who I say I am. And how does that happen? That happens with an attestation document that the enclave is able to provide. The attestation document is signed by the Nitro Hypervisor, which is part of the Nitro system we talked about. The document includes measurements like hashes of the enclave image, the application that's running in the enclave, the parent instance ID it's associated with, IAM roles of the instance, and many more. You could also use user-defined info like nonce that can be used as one of these hashes for you along with the attestation document. And lastly, the enclave also has cryptographic keys. So it can send the public key outside, retain the private key, of course. So when data, encrypted data, comes back wrapped in that public key, that is the specific enclave that can decrypt it. So these are all the benefits of using enclaves. So depending on the application that we talked about, and understanding that there are rules that go with it, with using the enclave, if you're clear on what we are protecting and who we are protecting against, the case to use enclave presents itself pretty smoothly. I'm going to touch a little bit on the Kms integration that we talked about. And this goes back to the cryptographic attestation. So this is an example, right? This is an example of what we have integrated. But you could use the same concept to attest enclave to any other service that you would like to integrate with your system. KMS is something we integrated. And the way this works is you set up a preset key policy, if you will, with KMS that is associated with the enclave, associated with the application that's running in the enclave. And then subsequently, when the enclave has to interact with KMS, it takes the attestation document that has all this information we just talked about and sends it to KMS. KMS then compares that attestation document against the preset key policy. If everything matches like it's supposed to, then the KMS can make a decision to reveal secrets to that specific enclave, and only that specific enclave. All through this, encrypted data is what will pass through everything that's in between KMS and the enclave. Because as we noted about prior to this, the enclave doesn't have the ability to interact with anything unless it goes through the parent instance, goes through that VSOC channel. So how does that data flow work? We'll piece it together in the next section here. So you heard us talk about the Nitro system, how EC2 instances are set up, what an enclave is, what are some of the rules to work with the enclave, and how plaintext data should only be revealed inside the enclave. But how does this all apply for a standard workload? What does this mean for data that's encrypted and sitting in your data lake? How are you going to bring it inside an enclave and process it? Let's take a look. Here's the scenario that we mocked up, right? So there are 3 players here. One is the data owner, the person who owns all of the highly sensitive data and possibly has the most to lose if that data is compromised. Then we have the system administrator who manages the life cycle of the instances of the enclave and everything, somebody who has access to everything, right? And then lastly, you have the developer, the person who's writing the application that's potentially running inside the enclave to process all of this sensitive data. The premise we are operating under is nobody trusts anybody, right? And there's no reason to. So let's continue that construct and see how we can bring in data, process it without anybody ever having to have seen anything. It's really a simple 3-step process that we deploy here, right? Fetch, send and verify, and receive. Right here in front of you, you have a diagram that shows our S3 buckets or data lakes, what you will. It doesn't have to be S3. It can be any data lake of your choice. We also show KMS as a service that we're using here. But again, if you choose to build your own KMS and integrate it with this, you could. This is an example flow, right? The assumption here is the data has already been encrypted. You've been responsible with your data. You encrypted it, stored it in an S3 bucket. When the application triggers, it's going to send the fetch command. What this does is brings data, encrypted data, from the S3 bucket along with its encrypted data key through the parent instance. The parent instance at this time is receiving everything in encrypted manner. So it's not seeing any plaintext data. It's only acting as a conduit to the enclave. The encrypted data and the encrypted data key comes from the data lake into the instance and then runs through the VSOC channel into the enclave. So the enclave has now received encrypted data and the encrypted data key. At the same time, it receives an attestation document from the Nitro Hypervisor. So now it has all this in its possession. So it's fetched and it's storing a few things right now at this point in time. And then it sends something. It sends the encrypted data key along with the attestation document to KMS. If you recall, when I introduced integration to KMS, I had mentioned that you have to set up the key policy of the KMS to what you're expecting to see from the enclave if you expect to reveal secrets to the enclave. So the assumption here is you have set up the appropriate key policies. So the KMS is ready, waiting with the appropriate key policy. Now the encrypted data key has been sent along with the attestation document to KMS. Now it's going to look at the key policy and match it against this attestation document it just received. If everything matches, then it'll take the encrypted data key and decrypt it. If it doesn't match, it's not going to do anything, so the secret goes nowhere. But if everything matches, it's going to decrypt the encrypted data key. And then it will re-encrypt that encrypted data key with the enclave's public key. So it's going to wrap it with the enclave's public key. And then comes step 3. It sends this re-encrypted data key back through the parent instance, through the vSOC into the enclave. So now if you take a step back and think about all these 3 steps, you will notice all of the communication that's happened, that went through the parent instance, was always encrypted information, whether it was data or the key. It's encrypted in some shape or form, but there's nothing plain text that's ever revealed to the EC2 instance. So now this re-encrypted data key comes back into the enclave. The enclave then takes that re-encrypted data key, uses its private key to decrypt the data key, and then uses that to decrypt the data. So now only the enclave sees the plain text data. Then your application can kick in to process plain text data within the enclave. Once all of that processing and computation is done, you can pretty much reverse this whole process. You can encrypt the data all over again and send it back to wherever you want to store it, depending on whatever you wanted to do with the data. But the key point here is the parent instance never saw anything plain text. The enclave was the only one in this data flow that saw plain text. So it's also from your side, your responsibility to make sure you're not transmitting plain text data from the enclave outside to anything else. While you decrypt it, while you process it, you want to make sure that plain text data stays inside the enclave. So hopefully that explains how a typical data flow looks like and what the application is expected to do with the data and the data keys. That's a sample flow, but what does this look like in real life? Where is it all pertinent, right? We talked about what is the data that you'd want to protect, who you'd protect it from, what a sample data flow looks like. But where is it being used today? Let me turn it over to Sudhir to talk to you a little bit about the use cases that we're seeing today and some emerging use cases we expect to see within the next year. Sudhir.
Thank you, Arvind. So far you have seen what Nitro System is, what Nitro Enclaves are, and the first-class integration that's available with AWS KMS, and a brief mention about ACM as well. So now let's go ahead and see what are the most prevalent use cases that we have seen customers use Nitro Enclaves for. And by all means, this is not the entirety of the use cases. These are the most common ones, right? So first and foremost, sensitive data processing. You have heard Arvind talk about what sensitive data is and the need to secure it using Nitro Enclaves. So sensitive data processing in this context is anywhere from a decrypt operation, a sign operation, or a tokenized masking, or even inferencing with your ML models, right? So any of these operations that you perform on datasets that are sensitive to you, Nitro Enclaves is a very good fit for it. And here is a quick visual on how that can be achieved, right? So as you see, your Amazon EC2 instance will still host majority of your application, even in case of sensitive data processing. And the little module, if you will, or the primary engine that decrypts and processes the sensitive data, that is what sits inside a Nitro Enclave. And as always, your sensitive data, the source of it could be Amazon S3 or any other data store, right? So the idea here is you will still have that secure local channel, which has been explained before, for those communication needs, right? So if you have to go retrieve that sensitive data from S3 or from DynamoDB or whatever data source, you use that secure local channel, bring it into Nitro Enclave, and then use it for any of these operations, right? So that's the most common use case that we have seen. Now moving on, multi-party computation. This is my favorite, right? So this is where you're just seeing that the sensitive data processing use case where maybe a single party, which is you, owns the data, right? But think about a scenario where multiple untrusting users or entities or companies own their own individual data sets, but there is value in bringing these data sets together and process them and analyze them and come up with data patterns. And that is a good use case, or that is the fundamental premise of multi-party computation, right? Collaborating together between untrusting parties and achieving an outcome. So Nitro Enclaves, as you can see here, is a very good framework or the design pattern to achieve that, right? So for example, party one can bring their encrypted data set and let a Nitro Enclave instance, right, using the platform configuration registers that Arvind has talked about and JD has mentioned about, can let a particular Nitro Enclave instance decrypt their sensitive data. And of course, before they do any of that, all the parties should come together, look at the Nitro Enclave code, and then sort of attest to the fact that yes, it's doing what it's saying, claiming it is going to do, right? So party one will let Nitro Enclave access their encrypted dataset. Similarly, party two will also let the same Nitro Enclave that they have looked at and attested before access their encrypted dataset. It comes together in this environment, and then think of operations like matching and lookup, and could be of any data processing need, right? So the Nitro Enclave is a very good fit for this sort of multi-party computation setup. Moving on, protecting IP, right? This is a very interesting and cool use case that we have seen customers use. So IP in this case is intellectual property, right? So think of a piece of code or machine learning model that you have come up with that you are trying to protect as an IP creator, right? And then, of course, once you create the IP, you want your consumers of the IP to be able to use that IP in a seamless fashion without jumping through too many hoops. So Nitro Enclaves we'll see in the next slide how Nitro Enclaves will solve that problem. But before we go there, I think there's a need to establish the roles here, right? As you can see here on the left side, IP provider. The primary responsibility of IP provider here is take their IP, build it, package it, compile it, right? And then pack it up into a bundle and essentially encrypt that bundle, right? This is where the security aspect comes. As an IP creator, IP provider, you want to protect your IP. And we'll see how Nitro Enclaves also helps an IP provider achieve that. But moving on to IP consumer, the primary goal of IP consumer is to consume the IP, right, for whatever the intended outcome is. And the idea here is, from a security standpoint, give assurances to IP provider that essentially this IP acts as the black box for them. They're just there to consume it and not to get into the internals of the IP and understand how it works, etc. Right? So these are the primary objectives from an IP provider and IP consumer standpoint. And if I move to the next slide, you will see how we'll satisfy both the objectives here, right? To the left-hand side, you will again see an IP provider's AWS account. So this is where, think of what I just mentioned before, right? You'll take the IP, you'll build it, bundle it, compile it, whatever the language-specific semantics are, you'll do all of that. And then the end result would be you will package up the IP into an enclave image file, right? So you'll encrypt the IP and put it in an enclave image file. And that EIF file is your fundamental primitive, if you will, that you will publish out, right? And this published EIF file is what the consumer will consume. So if you move on to the right side now, what the consumer will do, and this is a true black box experience, right? So the IP consumer will take that EIF file, instantiate in a Nitro Enclave enabled parent EC2 instance, and here comes the enclave at runtime, right? And just to give you an idea of what happens inside the enclave, if you look at the depiction here, all we are asking is for an IP provider to include a simple bootstrap application, and all the bootstrap application does is some of the steps that Arvind just mentioned in the previous slides, right? Which is take the encrypted IP, talk to KMS, decrypt the data key that's associated with that IP. And by the way, this KMS, if you look at the visual, is owned, managed, and the lifecycle is completely in control of the IP provider, right? So if you think of a provider experience, you know exactly who the consumers are going to be, and you choose to let them come in and decrypt the IP and consume it, right? So the total control is, again, back in the provider's hands. So moving on to the Bootstrap application, once it does that orchestration back with KMS and gets the decrypted data key, it is going to decrypt the IP itself, right? And then we'll continue on with the rest of the bootstrapping steps, which are unique to the IP that you are consuming here, or the IP that's in question here, right? So it could simply be run the ML model or run the piece of code that constitutes your IP. So that's how protecting IP is a very cool use case that we have seen. All right, now to the more complex stuff, right? So co-signing in blockchain. Now we are moving on to more multi-enclave solutions, right? So far we have seen how a single enclave is used in orchestration with KMS, etc. But here comes a use case where multiple Nitro enclaves can come together in a distributed computing framework, in a distributed computing setting, to work peer-to-peer, right? So here is a quick depiction where, and this is especially true in blockchain, where a multitude of co-signers will come together to sign a transaction, right? So for example, as you can see here, co-signer 1 is attesting itself to co-signer 2, and vice versa. So you have two co-signing nodes here which are aware of each other, which come together to sign a blockchain transaction, right? So this is a very, very, very good use case for a multi-enclave setup. Moving on, Nitro ACM, briefly mentioned in the features and benefits section. This is a solution that we have open sourced, where if you are in the business of maintaining web servers, and if you want to terminate the SSL connections coming in a secure fashion, Nitro Enclaves, the solution that we released using Nitro Enclaves, is a very good fit for it, right? What we have done is we have taken an Nginx web server and offloaded the cryptographic operations, specifically the PKCS11 engine, into a Nitro Enclave, so that the SSL keys that you use to decrypt the SSL TLS traffic are now secured inside the Nitro Enclave, right? So if you think about it, the entity that we are safeguarding here, and what we consider sensitive, are the SSL certificates, right? So right now we have a solution out there for Nginx web server. It's open source, so it could be adopted to other web servers as well, and we have Apache in the works as well. So that's Nitro ACM. All right. So these, like I said, these are the few prevalent use cases that we have seen customers use. We'd love to hear more as well. And now to continue with the discussion on NitroTPM, I'm going to hand it off to Arvind.
Thank you. I know you all got your hopes up when you saw them leave. We're not going to let you go. A few more minutes, all right? I'll close this out with an introduction to NitroTPM and UEFI Secure Boot. We are excited to see our confidential compute capabilities grow. And the latest in those capabilities was our introduction of NitroTPM. We announced general availability of NitroTPM in May 2022. So what is NitroTPM? Why is it relevant, right? A TPM is a security device that allows you to gather and attest system state, to store and generate cryptographic data, and to prove platform identity. So it brings with it a capability that did not exist with EC2 instances before. Now the EC2 instances can attest for themselves. You don't need an agent to run on it for you to attest and establish trust with it, with another compute entity you're trying to interact with. The NitroTPM uses our AWS Nitro System. Again, the foundation of everything that we talked about here. That's the basis on which NitroTPM is built. It allows EC2 instances to generate, store, and use keys without gaining access to it. That is important to understand here, right? Because you could be generating these keys, but if an admin gets a hold of that, then you can't really establish the trust without any fear here, right? So the instance itself does not get access to the keys that are getting generated. NitroTPM also conforms to TPM 2.0 specification. What this allows is for applications that are on-prem today and rely on TPM 2.0 capabilities to migrate to the cloud that much more easily. Some of the applications that we are looking at and hearing from customers are Microsoft BitLocker, just pure attestation capabilities, and Linux Unified Key Setup. Of course, there's a lot more TPM-based use cases and applications that are out there, but these are some of the more prominent ones that we are seeing today. NitroTPM can attest to the integrity of the EC2 instance by providing cryptographic proof via attestation mechanisms. So this is a feature you can take advantage of and leverage TPM capabilities if you're looking for secure attestation and authentication of the EC2 instance you're running. So similar to the capabilities that we talked about with Nitro Enclaves, now you have something that you can do just for your plain EC2 instances as long as they're Nitro-based instances that you have in your fleet. Along with NitroTPM, we also introduced UEFI Secure Boot. UEFI Secure Boot ensures that the bootloader is properly signed by a known authority. What does this give you? It builds on the existing secure boot process and provides additional defense in depth that helps customers secure software from threats across reboots. So if you're worried about rebooting and you're not sure about the state of the software that's left in there, that's what this is going to help attest to. So that's another new capability that we have launched along with NitroTPM. We encourage you to go and look at some of the blogs that we've put out there on this. I'll share some resources at the end of this session for you to go and take a look. So I don't want to bombard you with too many resources. There's just two that we thought we should highlight. One is the Enclaves page itself, from which you can gain all of the documentation access for Nitro Enclaves, and everything else associated with confidential compute should be linked from there. And we also have a self-help, self-paced workshop for you to go and get your hands dirty with Nitro Enclaves. It's a pretty easy to follow, nicely built workshop. And of course, if you try it, and if you have questions, you would like to reach out to us, we have contact information over there, so you can always reach out to us, and we'll be more than happy to get in touch with you to hear about your experience or help you with the workshop itself. I will turn it over to Sudhir for his closing comments in the session, and then you're home free.
Sorry about that. Took me a second to figure out the mic. But yeah, thanks for joining for this session. Hopefully you got an idea of the Nitro system, the two dimensions that we are solving for here, and the segregation of all the tools that are available in your kitty to solve for dimension 1 or for dimension 2. And the few things that I do want to leave with you is the Nitro CLI, the Nitro SDK, the Nitro Enclaves, the Nitro CLI, the Nitro Enclaves SDK, and the related tooling, right, that lets you build an enclave and put your application in it. Pretty much all of those source code is open source out there. So please do take a look at those repos. And if you have any questions, do use repost. That's our forum for asking questions and looking at what other customers are asking for. And if you have any cool use cases out there that you want to showcase, please reach out to us. We are definitely open to hear about new ideas. Again, thanks for coming.